Welcome to Brain Vision.
Hello everyone, this is the solution to problem 35 of chapter 24 of college physics. Here we're given the waveforms for the electric field and the magnetic field in an electromagnetic wave, and the general form looks like this. We're told that the E field is oscillating in the Y direction, whereas the magnetic field is oscillating in the Z direction. Also, looking at the waveform, we're asked to find as many of the properties of the wave as we can. So let's see what's happening here. So we see that the general form has Emax as the amplitude of the electric field and Bmax as the amplitude of the magnetic field, and these sit outside of the actual wave modulation of the field, which is this periodic function or any other periodic function. It could be exponentials, complex exponentials, or a sine wave or a cosine wave. There could be some phase here, but whatever it is, the amplitude of the wave sits out front. That's what's modulating the envelope of the wave, so to say. And so looking at the values that were given, we see that Emax is equal to 2.4 times 10 to the 5. Oops, excuse me, it's a bit far up. So 2.4 times 10 to the 5 newtons per coulomb. And we're also given Bmax, and Bmax is equal to 8.0 times 10 to the minus 4, I believe. 10 to the minus 4. Yes, 10 to the minus 4 Tesla. So these are the amplitudes of the electric and the magnetic fields, respectively. Now, looking at the waveform, we can also see that once you factorize 2 pi, the argument of the oscillating part of the function in terms of time is divided by the period, whereas the modulation in terms of space is divided by the wavelength. So this directly tells us that the period is equal to whatever is sitting under the variable t, and this is 1.5 times 10 to the minus 15 seconds. So this is the period of the oscillations. Then we can work out from this what the frequency is, because the frequency is simply 1 over the period. So this is 1 over 1.5 times 10 to the minus 15 seconds. So if you work this out, then the frequency is 6.7 times 10 to the 14 hertz. So that's the frequency of the wave. Now, as I said, under the space modulation of the argument of the oscillating function or the periodic function sits the wavelength. So you can also just directly read off what the wavelength is, and this is 4.5. So 4.5 times 10 to the minus 7 meters. So that's the wavelength of the wave. Now, additionally, you can tell that the wave is traveling in a positive x direction because there's a relative minus sign between the time and the space modulation of the periodic function in both cases. So you know that these waves actually correspond to each other. You can work out, if I have an electromagnetic wave whose electric field is oscillating in the y direction, and there's a magnetic field that's oscillating in the z direction, then I know that these two waves actually correspond to the same thing. It's the same wave. It's the same electromagnetic wave, but the different fields inside it. Now, additionally, you can work out what the speed of the wave is, because you can multiply lambda with f. This is true for any wave. So if you do this, then you get 4.5 times 10 to the 7, 10 to the minus 7, times 6.7 times 10 to the 14, and this is roughly 3.0 times 10 to the 8 meters per second. So you know that it's traveling at the speed of light. Now, one additional thing that you could look up is to see what part of the electromagnetic spectrum this frequency corresponds to, but we're not going to do that here. So as far as we're concerned, this is all of the things that you can read off. You can read of the maximum electric field, the maximum magnetic field, the period, the frequency, the wavelength, and the speed.